Hello all, my name is Ashutosh. I am a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we are going to discuss about the interference in your mobile communication. So these are the outlines. We're going to start up with the introduction where we're going to discuss about whatever we have studied in an earlier lecture. Then we're going to discuss the various interference effect in your mobile communication system. Then we'll basically going to discuss two major types of cellular interference that are existent, that is your co-channel interference and adjacent channel interference. We will going to look both of them into greater detail, that what are the causes and how we can eliminate them and how we will basically going to evaluate the effect. So we're going to take up both of them one by one. So in our last lecture, we have discussed about the handoff process. We have also discussed about the various taxonomy of your handoff on the basis of three parameters, that is technology used, in whichever technology they are being used, such as your CDMA or GSM, then different devices that has been used for this handoff process, that is we have studied about your network control handoff or your mobile assisted handoff, and also we have discussed about your link transfer, that is your intra-system handoff and your inter-system handoff. So now in this particular lecture, we are going to discuss about another important effect that basically limits the cellular system performance, and that effect is known as your interference. So what is interference? Interference is a fundamental nature of wireless communication system in which multiple transmissions often take place simultaneously over a common communication medium. So point is here multiple signals which will going to carry the same frequency component, they will going to transmit at the same time and at the same location. So if that is the case, then these signals will going to get interfere with each other, and at some places their amplitude will get added up and at certain places their amplitude will get subtracted. So overall impact of this particular effect is we will going to get some distortion in our signal. So interference basically limits the system capacity and increase the number of dropped calls. So now here we're going to discuss the effect of interference on our cellular communication into greater detail. We have already discussed that in our cellular communication we will be having two types of channel, that is your traffic channel and your control channel. Traffic channel would have been used to carry the user's information or data, specifically voice. And if we talk about your control channels, they will basically going to carry certain control information that are necessary to maintain that calls. So interference will going to cause the crosstalk from undesired users and noise in the background. If this interference will going to happen in our traffic channels, then this sort of effect might get observed. That is, we can observe multiple user signal over the same frequency band, and it may also deteriorate the signal quality. And if this particular interference will going to happen in your control channel, then what may happen? This sort of interference cause errors which results in the wrong instructions, such as your missed calls, your ongoing call might get dropped, or we can have certain blocked calls, that is we are initiating certain new calls but we are not getting the resources to connect the call. So these are the effects of your interference. So now we're going to discuss various sources of interference. So sources of interference might be another mobile phone in the same cell, a call in progress in the neighboring cell, if they are both working over the same frequency band, and it could be your another base station operating in the same frequency band. So if that be the case, then obviously signal will going to interfere and we will going to receive some distorted signal. Then your non-cellular systems leaks energy into the cellular frequency bands. So there are other systems also which will going to generate some RF signal leakage in the cellular frequency band. So all these might be the interference sources that will going to affect our communication system. So two major sorts of cellular interference that are existent in our cellular communication is your co-channel interference and your adjacent channel interference. Let us discuss one by one. So first one is your co-channel interference. Because of the frequency use, there are several cells that use the same set of frequencies. In our frequency planning, we have already studied the role of your frequency reusability, and if we will going to reuse our frequency bands, then definitely there are certain channels in our cellular system which will going to operate over the same frequency band. So those cells which are operating over the same frequency ranges or same frequency band, they are being called as your co-channel cells, and the interference produced due to that co-channel cells would have been called as your co-channel interference. So in order to reduce the co-channel interference, what we can do is co-channel cell must be separated by a minimum distance, since this is a basic signal propagation phenomena that with the distance your signal strength will get reduced. So here this particular figure is basically showing your co-channel cells which will going to have same frequency band for the operation, and this D1, D2, D3, D4, D5, D6, these are representing the co-channel distances. So if we want to contain that co-channel interference, then we must have to increase these co-channel distances. So when the size of the cell is approximately same, then the co-channel interference is independent of the transmitted power. Here what I wanted to say at this particular moment is, if all the cells will going to have same size, then in that particular case co-channel interference will going to become independent from the transmitted power. So let us consider a particular scenario where all the base stations will going to transmit their signals with the same power. So if that be the case and a particular user is connecting with a particular base station and it is receiving the signaling from its base station, and it is also getting some interference power from the other base stations, or you could say your co-channel cells base station. Since the distance is same, and suppose if a particular base station is trying to improve its signal to noise ratio via increasing its power, so in this particular scenario, if a particular base station starts increasing its signal power, then it will basically going to provide the noise power to the other base station. And if other base stations also doing the same thing, then in that particular case, after increasing sufficient amount of power, signal to noise ratio will not going to improve, although it will going to remain same. So that is why we are saying that if the size of the cell are approximately same, then in that particular scenario co-channel interference will become independent of the transmitted power. So co-channel interference will be the function of these two parameters, that is your R and D. Increasing the reuse ratio, that is Q is equal to D upon R, the interference is reduced. Here what we are trying to say is, if we are going to increase this particular ratio, that means we are going to increase this particular D by R, or you could say if we are just keeping this D increasing, then in that particular scenario your co-channel cells will going to become farther away from each other, and as they are moving away from each other, then this will basically going to limit the co-channel interference effect. Here Q is called the co-channel reuse ratio. So if the value of Q is larger, then it will going to gives us minimum amount of co-channel interference. This we have already studied. For your hexagonal geometry, your Q value would have been evaluated as under root of 3n. So a small value of Q provides larger capacity. As we have discussed that if the value of Q is larger, then in that particular scenario your co-channel interference impact will be lower, and if you are going to reduce out this particular value of Q, then obviously your cells will become nearer to each other, and to cover up the entire geographical region we have to further reuse the frequencies, which will definitely going to increase the capacity, but this will going to increase out your co-channel interference. So a large value of Q improves the transmission quality via reducing your co-channel interference. So a trade-off must be made between these two objectives, that is your co-channel interference is also get minimized, whereas your channel capacity might get maximized. So we must have to take the trade-off between these two objectives while designing our cellular systems. So here this particular slide is basically showing your co-channel reuse ratio for some typical values of n, where this n is basically representing your cluster size or number of cells lying in a particular cluster. So for these integer values I is equal to 1 and j is equal to 1, your cluster size n value will be equal to I square plus j square plus ij. While evaluating all this, we will going to get this value of capital N will be equal to 3, and by evaluating this under root of 3 times of n, that is root 3 times of 3, that turns out to be your 3. Again, if value of I is equal to 1 and j is equal to 2, this will going to gives us the cluster size value 7, and the co-channel reuse ratio can be evaluated as your under root of 7 into 3, that is your under root of 21, that turns out to be your 4.58. And similarly is the case for I is equal to 2 and j is equal to 2, and I is equal to 1 and j is equal to 3. So these are the typical values of your cluster size and your co-channel reuse ratio. So now this particular slide is basically showing how we are going to calculate this co-channel interference. So interference is nothing but it is your unwanted noise power that we really wanted to minimize them. So here let us consider that I naught be the number of co-channel interfering cells. So the signal to interference ratio for a mobile receiver can be expressed as signal power to the noise power, that will be equal to S upon summation I starts from 1 to I naught II. So where this S is basically representing your desired signal power and II is basically representing the interference power caused by the ith interfering co-channel cell base station. So if we're going to sum up all the other base stations which will going to contain the same frequency bands, that will going to provide us some interference, and the total interference power might be evaluated via adding or summing up all those co-channel cells. This particular figure is basically showing that this transmitter is transmitting with certain amount of power, and at a particular close-in reference point distance d0, we are observing this p0 measured power. So the average received power at a distance d from the transmitting antenna is being approximated by PR is equal to p0 times of d over d0 to the power minus n, where n is the path loss exponent, which may ranges between your 2 to 4 depending upon the typical scenario or typical atmospheric conditions. So via simple application of your Friis relationship, we may obtain that received signal strength can be evaluated with this particular formula. So if we're going to convert this particular thing into your dBm scale, then we may write it as your PR in dBm, that will be equal to P0 dBm minus 10n log of d over d0. So when the transmission power of each base station is equal, then signal to interference ratio for a mobile can be approximated as signal power to the noise power, that will be equivalent to R to the power minus n over summation I starts from 1 to I0 di to the power minus n from the last formula that we have discussed. That is, your signal power is proportional to R to the power minus n, and this interference power is directly proportional to distance of your co-channel cell to the power minus n, where this n is basically representing this exponent, and that particular reference point d0 will going to cancel out with each other, and we are left with this particular scenario. So consider only the first layer of the interfering cell. So if we closely observe about this particular cellular planning, here this is your reference cell and these are basically representing your co-channel cells. So obviously if that geographical region is quite larger, then we might have other 2 tiers or 3 tiers co-channel interferes also, but the impact of those 2 tiers or third tiers co-channel interference will be very lesser, so we can simply omit them. So here we are just being considering the impact of this 1 tier co-channel cell neighbors, that is this and this to this one. So considering only the first layer of interfering cells, we have this signal to interference noise ratio can be given as d over r to the power n upon I0, where I0 is nothing but it is basically representing the number of co-channel cells. We have already mentioned that ratio of d upon r can be evaluated as under root 3 times of n, where this n is nothing but it is your exponent. So for this hexagonal geometry, your signal to interference ratio can be evaluated as under root of 3n to the power n upon 6. So here in this particular figure, we are basically trying to consider the worst case scenario, where we are trying to say that these are your co-channel cells, this is our reference cell, where we are assuming that our user is basically going to lie at the boundary condition of cell boundary. So obviously its received signal strength from this base station is the least one, and it is also getting the interference power from other sources or other cells base station. So that will definitely going to reduce out its signal to interference ratio. So this is your worst case scenario, where we are basically trying to calculate the signal to interference ratio. So here, via applying this simple geometry, we have evaluated the actual or physical cell distances from this particular point to other locations of co-channel base stations. So the distance from this particular point to this particular cell turns out to be d minus r. This is your d minus r. This one is your d minus r upon 2. This is your d plus r. This is your d plus r by 2. And this is nothing but your simply d. So via simple geometrical manipulation, although we have already discussed about the basic geometry of your hexagon, that is all sides are equal, and if you will going to join the center of all the vertices, it will going to convert them into your 6 equilateral triangle. Specific properties of equilateral triangle also we have discussed all those stuff. So via simple manipulation or applying this simple geometry, we can evaluate the actual physical distances. And in our previous slide, we had already evaluated your signal to interference ratio, that will be equal to r to the power minus 4 upon 2 times of d minus r to the power minus 4. Since d minus r is the distance from your 2 co-channel interfering cells, that is this is d minus r and this is d minus r, plus d minus r by 2 to the power minus 4. One cell is having d minus r by 2, another cell is having d plus r by 2 to the power minus 4, then d plus r to the power minus 4 plus d to the power minus 4. So 1, 2, 3, 4, 5, 6. So this is how we will going to have the summation of interference power of all those co-channel neighboring cells. Here we are considering this exponent value is equal to 4, although we had already discussed that depending upon your physical scenario, its exponent value will going to lie between 2 to 4. So this is how we may evaluate the signal to interference ratio for our cellular system. So second one is your adjacent channel interference. So adjacent channel interference is basically caused by the signals from the neighboring frequencies. Here important term is your neighboring frequencies. Generally we might have got the essence that co-channel interference will going to happen due to the co-channel cells and adjacent channel interference will going to happen among the neighboring cells, but this is not be the case. Here important point is this is caused by the signals from neighboring frequencies or adjacent frequencies. So suppose in a particular base station we are using this particular frequency 1 to 6, and another base station we are using this 7 to 12, and another cell we are using this 13 to 18, and similarly suppose we just like this we have maintain our cellular planning. So the adjacent channel interference will going to happen between your this first cell. If a particular call is running over this sixth channel, it will going to get interfere with the another cells who is operating its seventh channel or seventh frequency for its call. So this particular interference will going to happen in these consecutive frequency bands. Particularly severe when the mobile is far away from its base station and very near to an adjacent channel transmitter, which is basically called or termed as your near far effect. So here in this particular scenario we are basically trying to say that the effect of ACI will be more severe if a particular mobile station is far away from the base station and it is actually nearing to a particular user who is operating into its adjacent frequency bands or transmitting into its adjacent frequency band. So here in this particular scenario, that particular user will going to get larger amount of interference power, which will going to basically impact its signal quality. So this adjacent channel interference also happens when a mobile close to the base station uses a channel or frequency band which is adjacent to a very weak mobile transmitting to the same base station. So here in this particular scenario we are observing that a particular mobile user is basically lying very near to the base station and it is transmitting over a particular frequency band which is also being used by a particular mobile user in the same base station who is lying at its cell boundary, and adjacent frequency bands they both are being using. So in this particular scenario, this particular mobile user who is basically lying nearer to your base station, if it is also transmitting with high power, then this will basically going to work as the interference signal for that user who are lying at the edge of the cell. So the impact of this adjacent channel interference might get controlled via power control mechanism. So this particular figure is basically showing that how adjacent channel interference will going to happen. Let us say that here these shapes are basically representing several frequency bands or channels over which your different users frequency signal might get pass it on. But the point is all the mobile equipment must have to utilize some filters in order to get a particular frequency band signal and reject all others. So let us say this is basically representing your filter response. So if this type of filter is there, although for ideal filtering the response should be just like your flatter one and this complete rectangle sort of stuff is there, or you could say that very high roll-off factor will going to have in our better filters, but here your typical filter response will going to look like this one. So if this is the filter response, then that mobile user will going to get this desired frequency component, but apart from that it is also getting these unwanted frequency signal band. These are your undesired signals which will going to interfere with your original signal and will going to deteriorate your received signal quality. So here we are basically trying to represent some of the reasons of your ACIs. Imperfect receiver filter allows nearby frequencies to leak into your pass band. This is what we had already explained, that is how imperfect receiver filter will going to have this adjacent channel interference. So here in this particular slide, we are trying to show you some of the ways by which you can limit the effect of ACIs. And what are they? Adjacent channel interference can be minimized through careful filtering and channel assignment. So first point is, if you're going to have this high quality filter, so that can very much reduce out this your adjacent channel interference. Apart from that, if we are properly doing our channel assignment, that is, we are trying to give us those frequency bands for the new call request which are not adjacent to each other. If via this particular thing we may plan or perform our channel assignment, it will substantially reduce out the impact of your adjacent channel interference. Keep the frequency separation between each channel in a given cell is as large as possible. So this particular point I was trying to explain you. So a channel separation greater than 6 is needed to bring the adjacent channel interference to an acceptable level. So obviously here also your quality factor will going to play an important role. Generally, if you talk about your typical receiver, and if we are in a state to provide the separation of more than 6, then we can limit the adjacent channel interference impact. And last one is your power control in all mobiles. So while discussing our near far effect, we have already discussed, that is how power control mechanism can reduce out your adjacent channel interference. Those users who are lying nearby your base station should transmit with lower power so that the interference impact for other users or the user who are lying far away from the base station might get receive lesser amount of interference power. So this is how we can limit your adjacent channel interference. So hopefully you guys have got the better insight about your co-channel interference as well as adjacent channel interference. Just in case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references. Thank you very much for your patient hearing.